Welcome to session 6 of Unit 3 in learning the course Design and Analysis of Algorithms. In our previous sessions, we seen various applications which are solved using dynamic programming algorithm design technique. We seen optimal binary search trees, matrix chain multiplication, 0 by 1 knapsack problem, multi-stage graphs, etc. In our today's session, we are going to see another application which is solved using dynamic programming, which is nothing but all pairs shortest path problem. The main objectives of this session are to understand what is all pairs shortest path problem, to solve all pairs shortest path problem by following dynamic programming. The learning outcomes of this session are, by listening this session, one can understand what is all pairs shortest path problem and able to follow dynamic programming strategy to develop algorithms for solving all pairs shortest path problem. The topics that we are going to discuss in this session are problem statement, that is what is the all pairs shortest path problem, and algorithm, what the algorithm that we are going to use to solve this particular application, and solving an example problem. Now coming to the problem statement, what is all pairs shortest path problem? Given a directed connected weight graph G, V, comma, E. Here G, V, comma, E is a graph. This is a directed connected weight graph. For each edge U, comma, V of E, a weight W is associated with the edge. That is, we already said that the graph G is a weight graph. Weight graph means each edge assigned some value. That value is nothing but weight of that edge or cost of that edge. Now, the all pairs shortest path problem is to find the shortest path from U to V for every pair of vertices in E. Here the all pairs shortest path problem is to find the shortest path between every pair of vertices in the graph. All pairs shortest path problem, here we are going to find the shortest path between all pairs of vertices. Between every pair of vertices, what is the shortest path that we are going to find. Now here for finding that shortest path between all pairs of vertices, we need to use a cost adjacency matrix. Now here how the cost adjacency matrix can be represented? The cost adjacency matrix of a graph G can be represented as cost of I, comma, I is equal to 0. That is traveling of a node I2 itself is to be considered as 0. Cost of I to J. So weight assigned to the edge Ij if that Ij belongs to edge set E. That is, if there is an edge from I to J, then cost of Ij is equal to weight assigned to the edge. If there is no edge between I and J, I is one vertex and J is another vertex. If there is no edge between those two vertices, in that case, cost of I, comma, J becomes infinite. So here we can represent the cost adjacency matrix with the three values. Those three values are 0, infinite, and weight assigned to the edge. Here 0 is when cost of I, comma, I, so that is cost of 1 to 1, cost of 2 to 2, cost of 3 to 3, like that, cost of n to n, which becomes 0. And cost of Ij becomes infinite if edge is not present in between the vertices I and J in the graph, and it is equal to weight assigned to the edge, that is Wij, if there is an edge between the vertices I and J in the given graph. Coming to the time complexity of all pairs shortest path problem, this can be solved with the time complexity big O of n cube. Here the time complexity of all pairs shortest path problem is big O of n cube. Now here you can see an example for this all pairs shortest path problem. Here I given an example of just simple one pair of vertices. Here I taken one vertex as the source and remaining vertices as the destinations. What becomes the shortest paths from the source vertex to all remaining pairs of vertices? So here we consider one as the source vertex and remaining all becomes the destinations. 2, 3, 6, 5, 4 all becomes the destinations. What are the shortest paths? Here this is the shortest path and this is the shortest path for 3 and this is the shortest path for 6, like that. So we represented all shortest paths. Next, coming to the example how to represent the cost matrix. Now here I given a graph with 4 vertices. Those 4 vertices are represented as A, B, C, D and I given some edges between those vertices and those edges are assigned with some weights. Now how to write the cost adjacency matrix for this particular graph. So let us see the cost adjacency matrix. Here this gives the cost adjacency matrix for this graph. Now I already said you that cost of I comma I becomes 0. That is cost of traveling A to A which becomes 0. Cost of A to B. So if there is an edge between A to B, what the weight we assign to that edge? That weight is to be represented as the cost between A and B. Now here you can observe there is an edge between A to B. Here this is a directed graph. Let us see here this edge is the A to B and the weight assigned to this edge is 4. So here the cost of A to B is 4. In the same way, cost of A to C is 1. Cost of A to D is 3. Here there is a direct path from A to D. Cost of A to D is 3. Now coming to B to A. Here there is another edge from B to A whose cost is represented as 15. Now B to A becomes 15. Now cost of traveling from B to B is 0 and cost of B to C is 20. Cost of B to D is 10. Now in the same way C to A, if you observe C to A, there is an edge between C and A. Now here the weight of that edge is 9. Cost of C to B. So since there is no path from C to B, there is no direct path from C to B, we can represent its cost as infinite. And traveling from cost of C to C is 0 and cost of C to D is 1. In the same way, D to A, there is no direct path from D to A. There is no edge between D to A. So that's why its cost is represented as infinite. And cost of D to B is 4. Cost of D to C, there is no path, there is no edge from D to C. So it also becomes infinite. And here cost of D to D is 0. Now here, what is our problem? What is our all page shortest path problem? Here we need to consider every vertex as a source vertex. That is, suppose if I am taking A as the source vertex, B, C, D becomes the destinations. Now what is the shortest path from A to B? What is the shortest path from A to C? What is the shortest path from A to D? In the same way, we need to consider B also as the source. In this case, A, C, D becomes the destinations. What is the shortest path from B to A, B to C and B to D? Now here if you consider C as the source vertex, what is the shortest path for A, B and D? That is the shortest path from C to A, C to B and C to D. The same way if you consider D as the source, the destinations becomes A, B, C. What are the shortest paths from D to A, D to B and D to C? Now we need to find all these the shortest paths for all these. What is the shortest path we need to find, and we need to update that cost matrix with shortest paths. So here this cost matrix contains the original values where the edge is present, but we need to find the path. Suppose for example C to B, there is no edge, we represented its cost as infinite, but via some other vertices we may reach from C to D, C to B. So that's why there is a path from C to B. So that's why what becomes the cost to reach B from C? We need to find that cost and we need to update this infinite value with that cost value. So this is our entire all pairs shortest path problem. Now here let us see. For the same example, I represented manually what are the shortest paths and what are their costs. Let us see here A to B. So if you observe here A to B, I can move from A to B directly with the cost 4, or I can move A to C, C to D and D to B with a cost of 1 plus 1 plus 4, which becomes 6. So out of these two paths, so here I have a path A to B and also I have a path A to C, C to D, D to B. Two paths are there from A to reach B. So this path takes a cost 4, this path takes a cost 6. So out of these two, which becomes the shortest path? This becomes the shortest path since its cost is less. So here I represented its shortest path is A to B and its cost is 4. In the same way, A to C. We can reach C from A with a cost of 1. So here also there is a direct path. And coming to A to D, here I have a path from A to D whose cost is, there is a direct edge from A to D whose cost is 3. But I can move A to C, C to D. Here A to C cost is 1 and C to D cost is 1 whose value is 2. That is, I can move from A to D with a cost 2 via C. So that's why this becomes the shortest path. This becomes the longest path. So here I am representing the path, the shortest path from A to D as A to C, C to D whose cost is 2. And coming to B to A. Coming to B to A, the shortest path is 15. And coming to B to C, here I have a path from B to C whose cost is 20. From B to C whose cost is 20. But I can move B to A to C. B to A to C with a cost of 15 plus 1 which is nothing but 16. So that's why B to A to C, even though there is direct edge from B to C, we cannot consider that as a shortest path. So we can consider the path from B to A and A to C which is completed with a cost 16. So this is considered as the shortest path. So in the same way I represented B to D, C to A and C to B. So coming to C to B, there is no path from C to B. So here I can reach C to B via C to D and D to B with a cost 5. So in the same way, D to A, there is no direct path from D to A. So its cost is actually infinite. But we can reach D to A via the vertex B. So its path, its cost becomes 19. D to B, in the same way, D to C. How I can reach D to C? D to B, B to A to C. So here, even though there is no direct path from D to C, I can reach D to C via the vertices B and A. So that's why its path, its cost becomes 20. So here all these gives the shortest paths between all pairs of vertices. So here we are going to find the shortest paths between all pairs of vertices. Here we are taking A as the source and B, C, D becomes the destinations. B as source, A, C, D becomes destinations. C as source, A, B, D becomes destinations and D as source, A, B, C becomes destinations. So we found the shortest paths between all pairs of vertices. Now here since we given a small graph with 4 vertices, it is possible for us to write manually all the shortest paths, but it is not the case if the number of vertices are increased. So in that case we need to go for the generalization, that is we need to develop an algorithm to solve that particular problem. So that's why what becomes the algorithm for this all pair shortest path problem. Now let us see. Here by following the algorithm and by updating the costs, the final shortest path matrix becomes this one. So how we can obtain this matrix, this shortest path matrix? So we can see that by explaining the algorithm. Now let us see the algorithm. Here this is the algorithm which is developed by following dynamic programming to find the shortest paths between all pairs of vertices in the given graph. Now let us see the algorithm. Here we are passing 3 parameters to the algorithm. What are those 3 parameters? Cost, A, N. What is this cost? Cost 1 to N, 1 to N, which is a cost adjacency matrix. So which is written for N number of vertices. And A is the matrix that shows all shortest paths. That is the final matrix that we are obtaining after processing or after analyzing the algorithm. So here the first one is cost adjacency matrix and A is the matrix which represents all shortest paths. Now let us see. For I is equal to 1 to N, for J is equal to 1 to N, copy cost matrix to A. So what we are doing here? Here we are initially doing copying cost matrix directly to A. So here what is the shortest path matrix that we are going to find? To that matrix, we are first copying the cost matrix. So later we are going to update that matrix A by following this formula. So what the formula we are following? Let us see. For k is equal to 1 to n, for I is equal to 1 to n, for j is equal to 1 to n, Aij is equal to minimum of Aij comma Aik plus Akj. That is what it indicates. Here we are representing two terms. One term is Aij and other term is Aik plus Akj. Out of those two, which becomes minimum? With that minimum value, we are going to update this value. Aij value we are going to update. Now that is, what is the actual value of Aij? Here Aij represents what is the actual value of Aij. That is, if there is an edge from I to j, it becomes Wij, or if there is no edge, it becomes infinite. That is the original value of Aij. Now what this represents? This term represents Aik plus Akj, means if I moved from the vertex I to k and k to j, if I moved from the vertex I to k and k to j, then what becomes the cost? So suppose if that cost is W dash ij. So here the first cost is Wij and the second cost is W dash ij. Out of these two terms, which becomes minimum? That minimum value is placed in the place of Aij. That is, that value is updated in the matrix Aij. That is, we are finding whether the cost is minimum if we are traveling directly from I to j, or if we are traveling I to k and k to j. That is, we are traveling I to j via vertex k. So what becomes the minimum? Whether this is minimum or this is minimum, we are going to find. With the minimum value, we are going to update the matrix. So finally we are going to find this value. We are returning A, which is nothing but shortest path matrix. So here I am going to explain this algorithm by taking an example. Let us see that example. Now here the same graph we taken in this for explaining that algorithm. Now here let us see first what we are doing. For I is equal to 1 to n, for j is equal to 1 to n, copy cost matrix to A. Directly what the cost matrix that we obtained for this graph, that is directly copied to A. Now here cost matrix is copied to A. Here this becomes the cost matrix. Here this becomes the cost matrix. That cost matrix is directly copied to matrix A. Here this is the shortest path matrix. This is A. We need to update the values with the shortest paths. In this matrix we need to update the values with shortest paths. Now here what is the second part? Now the second part of algorithm is we need to find the minimum cost. We need to find the minimum cost. Now here what is the minimum cost? What is the updatable value? That we need to find here. Now let us see. For k is equal to 1 to n. Here what is n? N is the number of vertices. How many vertices are there in the given graph? 4 vertices are there in the given graph. So for k is equal to 1 to 4, for I is equal to 1 to 4, for j is equal to 1 to 4. Okay, now that means first of all, for doing this one, for implementing or for analyzing this step, first we need to find what the various cases that are obtained because of these 3 for loops that I am going to explain. So first let us see. For k is equal to 1 I am taking. For k is equal to 1 I am taking. If you enter into the loop here, for I is equal to 1. I is equal to 1. Now I entered into this for loop. For j is equal to 1. Now when I come out of this loop, when j becomes 4, then only I can come out of this loop. So first I implement or I analyze the algorithm for j is equal to 1, then I analyze the algorithm for j is equal to 2, then I analyze the algorithm for j is equal to 3, then I analyze the algorithm for j is equal to 4. After j is equal to 4, we go for upper loop. Here when I come out of this loop, when I becomes 4, that is in the second case I becomes 2. Again I come to j. J is equal to 1, j is equal to 2, j is equal to 3, j is equal to 4. So like that we need to do the algorithm. So what the various cases that we are obtaining for these 3 for loops, nested for loops. Let us see the different cases. Now first, when k is equal to 1, I is equal to 1, j is equal to 1. Now when I come out of that loop, when j becomes 4, that is j is equal to 2, k1 i1 j2, k1 i1 j3, k1 i1 j4. So after that I value is to be incremented, that is k1 I2 J1. When I can now come out of this loop, after J value is 4. So K1 I2 J1, K1 I2 J2, K1 I2 J3, K1 I2 J4. So after that I can come out of this loop. Again I am going to this loop. Here I value is incremented. I value becomes 3. That is K1 I3 J1. K1 I3 J2, K1 I3 J3, K1 I3 J4. Now here I can come out of the loop and I go for this loop. Here in this loop I value becomes 4. Now that is k is equal to 1, I is equal to 4, j is equal to 1. Now in the same way 2, 3, 4. Now I can come out of this loop. I can come out of this loop and this loop is also completed. I value already became 4. So this also completed. So I came here into this loop. Here in this loop k becomes 2. Now here in this case, what the various cases that are present? K is equal to 2, I is equal to 1, j is equal to 1. Again it starts. So for each k value, how many conditions that we are obtaining? We are obtaining 16 conditions. For each k value we are getting 16 cases. Now here for k is equal to 1 we have 16 cases. For k is equal to 2 we have 16 cases. For k is equal to 3 we have 16 cases. And for k is equal to 4 also we have 16 cases. By analyzing all these 16 cases, we can update the matrix A with the shortest path matrix. Now let us see how to analyze all these 64 cases. Okay, let us see the first one. Here this is the cost matrix. Now this is our algorithm. Now what is the first case? What is the first case? K is equal to 1, I is equal to 1, j is equal to 1. Now what the algorithm I need to follow? A, I, j. I means 1, j means 1, which is equal to minimum of A, I, j. A, 1, 1, comma, A, I, k. Here all are ones. So since all are ones, we can write directly this one. This is minimum of 0, comma, 0 plus 0, which becomes 0. So you can understand one thing, never these values are updated. Never these values are updated. So that's why you need not trace this one, ij values as equal. So whenever you find ij values are equal, I is equal to 1, j is equal to 1, I is equal to 2, j is equal to 2. I is equal to 3, j is equal to 3, I is equal to 4, j is equal to 4. Those values need not be traced or analyzed. So this also need not be analyzed. Next, this also need not be analyzed, and this also need not be analyzed. In this case, the values cannot be changed since the cost of traveling from A to A, B to B, C to C, D to D is 0 obviously. So even we analyzed, we will get the same thing. So that's why need not analyzing those things, right? So coming to the second case, what is the second case? K is equal to 1, I is equal to 1, j is equal to 2, K1, I1, j 2. Now here how I can solve this one? Aij, that is A12 is equal to minimum of A12 comma Aik, I is 1, k is 1 plus Akj, here k is 1, j is 2. So that is minimum of, what is A12 value? 12 means here AB, cost of traveling from A to B. Here you can represent these as 1, 2 also. 1, 2, 3, 4. This is 1, 2, 3, 4. Now 1, 2, cost of traveling 1 to 2 is 4, 4 comma, cost of 1 to 1 is 0 plus a 1 to 2. 1 to 2 is again 4. Here we will get the value as 4. That is, it is not updated. This value is not updated. Now we will go for another case. Now we will go for the next case, which is nothing but k is equal to 1, I is equal to 1, j is equal to 3. Now in this case, what we are going to find? A13. A13 is equal to minimum of A13 comma Aik, that is A11 plus Akj. Kj is 13. So what is 13? Cost of 13 is 1. 1 comma 0 plus 1, which cannot be updated again. Now next one. What is the next one? A14, cost of Ij, that is I is 1, j is 4, A14. In this case, minimum of A14 comma A11 plus A14. So here A14 is 3 comma 0 plus 3. So here which value is not also be updated. Now I am going to the next one. K is equal to 1, I is equal to 2, j is equal to 1. That is Aij, I is 2, j is 1, 2, 1, which is equal to minimum of A21 plus Aik. So here I is 1, I is 2, k is 1. That is A21 plus Akj, k is 1, j is 1. So here also 2, 1 is 15 plus 15 plus 0. Here it becomes 15. It cannot be updated. Now in the same way, you can solve all the remaining cases to update the values in the cost. In the same way, you can analyze all the cases to obtain the updated shortest path matrix. Now here if you can see here the cases are changed here. So by changing all those cases, you can analyze the matrix. Now here you can see the matrix. Here you can see the updated matrix. Here the matrix is updated. So here the cost of moving from A to D is updated as 2. Actually the cost of moving A to D is 3. It is given as 3, but by analyzing that algorithm, it can be updated as 2. And cost of moving B to C. Here we have B to C. We can move B to C through 20, but its cost is updated as 16. And cost of moving C to B. C to B, there is no path, but actually its original value is infinite, but here its value is updated as 5. Now cost of D to A. D to A is also, there is no path, actually its value is infinite, but its value is updated as 19. And cost of moving D to C. D to C is also updated as 20. Actually there is no path from D to C, its value as updated. By analyzing that algorithm, you can get all these updated values into the shortest path matrix. I hope you all understood what is all pairs shortest path problem and what about the algorithm and how to solve this problem. Now I am going to summarize the concepts what we explained in this session. In this session we explained about what is all pairs shortest path problem, what is its statement, and also how to solve that particular problem manually, and also we seen an algorithm which is developed by using dynamic programming to find the shortest paths between all pairs of vertices in the given graph. We also seen an example problem how they are updated, how the values can be updated. To assess yourself here, I given some questions. Please answer these questions. The first question is, the algorithm followed to solve all pair shortest path problem is option A, Distrauss algorithm, option B, Floyd-Warshall's algorithm, option C, Prim's algorithm, option D, Krishkal's algorithm. Algorithm design technique followed in solving all pair shortest path problem is option A, divide and conquer, option B, greedy method, option C, dynamic programming, option D, backtracking. Solve the all pair shortest path problem for given adjacency matrix graph using Floyd's algorithm. Now let us see here. I given a cost matrix. Here I did not given the graph. Directly I given the cost matrix. You need to find the shortest paths. So here this matrix contains 5 vertices. Those 5 vertices are represented 1 to 5. Those 5 vertices are represented from 1 to 5. You need to find the shortest paths from every pair of vertices, between every pair of vertices. That is, first you need to take 1 as the source. You need to consider 2, 3, 4, 5 as the destinations. In the same way, you need to consider 2, 3 and so on. Like that you need to consider. Every vertex becomes the source and every vertex becomes the destination. Okay. So, right. In preparing this presentation, I used the digital content from various public sources. It is only used for educational purpose and not for the commercial purposes. Thank you for listening the session.